ExoMars is going to be the first true from the start autonomous vehicle trained to understand its environment with minimal human interaction. So another interesting thing is you've actually worked on the navigation systems of Martian rovers. So tell us a little bit about that.
So a very long time ago, when ESA first decided it was going to do what is currently called the ExoMars rover mission, which will launch in a couple of years, I was tasked with a team at BAE Systems to figure out if it was actually possible to deploy an autonomous navigation system on a Martian rover, because believe it or not, the compute capabilities of these things is very low. It's like having a 1995 desktop computer from like 1995.
So these things initially, so talking about the older Martian rovers, they weren't actually true autonomous vehicles.
I believe ExoMars is still going to, it's late now, so it might have been overtaken by a NASA mission or something, but it was supposed to be the first fully autonomous Martian rover. In fact, I think Spirit and Opportunity, I think while they were launched as remote control rovers, I think they might have had some over-the-air software upgrades over the years and have some autonomous capability. But ExoMars was supposed to be the first from
fully
the beginning.
Autonomous from the beginning. So yeah, that must have caused a problem in the older missions with just the flight time of... You've got to have a video come back from Mars. The guy sat there in the control room.
So the round trip time of your radio signal to Mars, at best, is 6 minutes, depending on where Mars and Earth are in their orbits at the time. And so, yeah, if you're driving this Martian rover and you turn around a boulder and suddenly realise there's a big crevasse there... and you pull back on the brakes, 5 minutes 55 seconds ago, the rover hit the bottom of the crater.
Yeah.
So they traditionally have all crawled over the surface like
to allow that reaction time and that flight time, just so that you don't end up in a huge hole.
And from memory of talking about it all those years ago, it was always sort of drive forwards a little bit, stop. So it wasn't even continuous anyway. Because
to allow for that assessment to happen.
Exactly, assess the scene, any information from the sensors about whether the sands might be getting softer, because you also don't want to get stuck in soft sands. That's the killer, obviously. One of the NASA rovers is now a stationary platform because it's just stuck in some soft sand. So that was the issue with teleoperation. And you think, okay, fine, it's easy, right? Just make it. There's no pedestrians running out in front of a Martian rover.
Well, you say that.
Bert, the Martians are here, Bert. What'll we do, Bert?
Hopefully, maybe.
But the challenge is that here, outside this window, we have the luxury of being inside the Earth's atmosphere and protected by its magnetosphere, and cosmic rays get blocked from hitting us by various parts of the atmosphere, and we're protected by our magnetic shield. And on Mars, you don't have that. So you have these really high energy cosmic rays that are getting all the way down to the surface. And a high energy cosmic ray hitting my smartphone would flip loads of bits inside it and just change the state of the program running in memory and just crash it, basically. No pun intended on crashing the Martian rover with a cosmic ray muon. But anyway, so what happens is space qualified computers are really, really thick, chunky pieces of silicon, but physically very thick.
Yeah.
So that the
just as a physical shield, basically. Yeah.
There's loads of stuff that stops the high energy particle before it can get down to the part of the chip that's actually holding the current state as a 1 or a 0.
Yeah.
And so, unfortunately, the nature of the beast is if you're making chips that still look like they're off of the 80s, they're still behaving like they are too.
Big shoulder pads and big hair, and
you haven't got this incredible tiny transistors all over the place, miniaturization going on. You've just got massive processors, and so the radiation hardened computer that's used in Martian rovers has something like a 200 megahertz processor, and I think it had more than 1995 grade of RAM. I think we had like 256 meg of RAM or something to play with. But basically, if you're going to design an autonomous navigation system that has to process all the sensor measurements, do intelligent things, make clever decisions, is 200 megahertz enough? Oh, by the way, sorry, you don't get the whole 200 megahertz processor yourself. We're going to do some science as well.
Yeah.
By the way, you're not just
we're not just getting there to have a joyride and go around. Yeah.
Exactly. So there's all the budget to assess about the science that would be going on at the time. We had all of these things we had to deal with where we assessed, well, how about if we do steal the entire computer for a certain amount of time, and then we'll turn it off and let it do the science, and then we'll come. Yeah. So we had to plan all of this.
It's sort of like that scene in Apollo 13 where he's laying under the rocket and trying to work out all the different ways that you could fudge stuff together so that we can actually get enough power to do a certain activity.
Ken, you're telling me what you need. I'm telling you what we have to work with at this point. I'm not making this stuff up.
They're going to need all these systems, John.
We do not have the power, Ken. We just don't have it.
Exactly. There's so many constraints on it in terms of, like you said, the processing power. And I guess the weight of the package, and you've got to have the solar panels on there to bring the energy for whatever thing you want to do. So it's it really is a balancing. You've got your hands tied behind your back, really.
Yeah, exactly.
What you're trying to do.
Yeah, it's kind of thing where people might casually think, well, just put 2 of those computers on.
Yeah.
But that's then weight.
Yeah.
And more solar panels.
Yeah.
Which is more weight.
Yeah.
And weight is fuel, and fuel's expensive.
Yeah.
The rocket might not even be capable of carrying that much weight.
Yeah.
So it's now $1 billion more expensive.
Yeah.
Oh, okay. We'll go back.
We'll shelve that.
We'll go back to one computer then.
Yeah.
So we had all of this fun of trying to. It was exactly like that. What is the budget of
so when I'm trying to do my fantasy football team and I can't crowbar all the players that I want in there.
Yeah. And so we looked at all the sensors that were already going to be on the platform, which ones we could reuse for navigation purposes that were there for science. And so inevitably you end up, because there's cameras on the rover, we came to the conclusion that you would be able to use a binocular camera-based navigation system. And we were looking at using what's called SLAM, simultaneous localization mapping, so that the robot could build up its own map of the environment. It's not that important because there's so much good imagery of Mars that you weren't needing to build up your own map. There was already a map you could work to.
So ExoMars is actually being trained on actual visuals of Mars.
Well, the Seeker navigation system they use, I believe, is still vision-based. It will have evolved a lot since this early design stage.
Yeah.
This was really, go or no go. Do we bother trying to do a autonomous navigation system on the rover? Is it possible with that set of constraints? And we did conclude it was possible, and it continued. So the idea that we were working with at the time was that the people wanting to do the science could just go, click, 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 click on satellite imagery of Mars and go, these things are interesting, so go and investigate those. And the Martian rover would understand what it's looking at versus what those clicks are on a top-down view, and drive to those places and keep an eye out along the way for shiny-looking objects and ETs, trainers they've left behind, and all that kind of stuff, and not fall into crevasses or collide with any boulders.
So I think it had some training, or it is having some training on the Earth as well, as to what interesting structures are in there.
Yeah, so it was tested in, I think, Tunisia.
So they send it out into the Tunisian wilderness, and it sort of drives around for itself, understanding what a crevasse is.
From memory, I think the challenge, used to have these really cool names for things. I can't remember, maybe we'll come back to it later. But the sort of the challenge was basically go find a few golf balls.
Yeah.
Was, the goal of the autonomous, one of the proposed autonomous tests. They would go and identify where these golf balls were scattered around some Earth terrain.
They had quite a fun story actually about one of the other physics problems was dealing with soft sand, which might be difficult for the computer to ascertain that just from the visuals, that is quite soft sand.
Yeah, and this was one of the things where we were trying to understand which other sort of sensors on the platform could help us to understand what might be soft sand.
Within all the constraints, again, of those memory constraints and weight constraints.
All sorts of stuff, like if you were allowed to just shove some whiskers on the front of this thing and watch.
So imagine the
behaviour.
Martian coming along, and what the hell is this thing? This
Exactly.
huge cat coming down.
And whiskers are pretty good in nature, so and they're cheap. I think I probably proposed a grappling hook just to pull yourself back out of any
The old
problems.
Batman approach at the back.
Yeah. I believe there's been suggestions. I don't know if this is what they're going with now, but at some point there were suggestions of literally just another little like a sacrificial robot that drives in front, and if it
Just
goes
like,
I'm in trouble, then ExoMars doesn't carry on behind it. So anyway, soft sand is still an ongoing problem. If anyone out there has solved the soft sand problem, please let us know. Yeah, it was great fun, and there was another interesting sort of centrifusion navigation-y story about ExoMars. A few years ago, there was a prototype version launched that was going to test a few bits and pieces, and the mission has created the crater that is, I think, now called the Chaparral crater on Mars. Or there was already the Chaparral crater that it's now made a dent in. I can't remember, but it's a very interesting sequence of events. So it was a partial success, as they like to call these things, and what happened was that when the parachutes opened to
Slide out
arrest
onto the Martian
everything,
surface,
the system swung around much more than anyone had expected it was going to. And the gyroscopes inside the sort of descent part of the navigation system saturated, which means that they were only capable of reading up to like 99999 or something, and they needed to read a bigger number. And so all they could do is report that saturated value. And what happens with gyroscopes is you add up the numbers coming from them in order to assess your current orientation. So it was adding too small a number during that process. And so when all of the swinging around and carnage calmed down, the wrong numbers had been used in the calculation of the current orientation of the platform. And unfortunately, the navigation computer thought it was almost completely upside down, and it wasn't. It was obviously still just dangling from the parachutes, but it thought it was this way. And what happened next was it turned on the landing radar to determine how high it was above. And what it was obviously going to do is assess, based on the radar returns, when it should cut the parachute, all this kind of stuff. Now, because it thought it was upside down, when the radar starts pinging and radar returns start coming back to the platform, it thought it was like minus 13 kilometres beneath the surface, which obviously wasn't, or however high it was, whatever number. It was thinking it was at a massive negative altitude when it was actually at a massive positive altitude. And unfortunately, the way the sort of programming worked was it went, is my altitude currently less than like 0.5 metres? Yes, cut the parachutes off and deploy the legs. So way too high. It went through the process of sort of shedding the parachute and pushing the rover out, which then sort of went through a jolly freefall, trying to deploy its science instruments. So there's a lovely report which has lots of silver lining statements in there, like the impact was a bit faster than it should have been, but it was near where we wanted it to be. And the science instruments did successfully deploy and transmit some information for like 5 seconds before they were catastrophically destroyed. But it was another lovely example, and there's been many instances like this. It's very tricky to send stuff to Mars. There's been lots of examples like this where it's the most frustrating, silly little thing that just destroys the entire mission. And it is often a centrifusion issue, a navigation issue, some aspect of the calculations of getting the thing down there safely. It just shows that even though we send lots of stuff to Mars, and we can land men on the moon, and we can build autonomous aerial vehicles, and we can make cars drive around the streets on their own, it's still possible to unfortunately spend an awful lot of time and effort designing this thing that's got to get to Mars, and have brilliant people from all over the world designing them. And you still have this issue where, has anyone thought about what will happen if the gyroscope saturates?
Yeah.
I wish we had done.
Yeah.
But they will for next time.
Yeah. Same idea you were saying about with the improving things like they have in the aviation industry. Try and learn from that problem. Like dumping Beagle into a crater, I think. The Martians must be thinking, why are you sending all these things and just dumping them in craters? They seem completely useless. So, I mean, in summary, ExoMars is going to be the first true from the start autonomous vehicle trained to understand its environment with minimal human interaction. So it's not going to be joysticked from America or wherever else.
It's an ESA mission, so
yes.
somewhere in Europe.
Yes, it's not going to be on a joystick from somewhere in Europe. It's actually going to be trying to understand its own environment, drive around, which actually, I guess, means that it can drive around quicker and do more work in a set period of time, because we don't have this travel time. It's learning on the fly as it's there on the ground.
Yes, it'll be able to cover a vastly larger area of Mars and do much more science, because it can move much more quickly in the boring bits.
So that's one of the exciting promises and the improvements that we can get with this machine learning and with these autonomous vehicles.